In our last lecture, we did hypothesis testing for the mean, and our standard deviation was known. And we saw that there was a lot of repetitiveness between doing hypothesis testing and doing the confidence intervals. The same thing is true here. We're going to do hypothesis testing for the mean, but for our sigma unknown. And this time, we're not going to even find p-values. We're only going to use that method where you're looking at the critical region. Okay, so let's get started. So like I said, we've done this before, okay? There's not really any new content here other than let's come up with a conclusion about our hypothesis, okay? So we're going to use a t-distribution. So you're going to need your t-charts, which I included with this lecture in the board notes. Okay, so what do we need to do? We need to specify a level of significance, which, like I said, is if you're running your own study, then that's something that you decide, whatever is acceptable to you. In most of these problems, it's given to you, so you don't have to worry about making that decision. And remember that level of significance is, the notation for it is alpha. Okay, it's typically 0.1, 0.05, 0.2 even, and 0.01. And in these t-distributions, you'll also see in the t-chart that you might have an alpha that's equal to 0.02, okay? Then you also need to identify the degrees of freedom because this is a t-distribution, and depending upon the degrees of freedom, that's going to change the curve. Remember, t-distribution is not one curve like the normal distribution. It's a family of curves, and each curve has a different degree of freedom. So we need to identify that. And that we just abbreviate with a DF. And if you remember, that's equal to n minus 1. Okay, it's n minus 1 because that's the number of variables that you have a choice about changing. Okay, whereas that very last variable, if you're finding, let's say, the mean, right? If you have 10 numbers and you have a mean that you need to get to, you need to have a mean of 20. The first 9 numbers can be whatever you want, but the 10th number is fixed, okay? 10th number is fixed. Once you have the first 9, there's only one possibility for the 10th number in order for you to get a mean of 20. Okay, and then you need to find the critical value. So we did that with the z-score chart, right? We did that with the z-score where we found the critical value. Here we're doing it with the t-distribution. And not surprisingly, that critical value is annotated as T0. Okay, so how do we do this? Well, we do have the t-chart gives us a little bit more information than the z-score chart, okay? It's a little bit easier to use in some ways. So let's just go through what we mean by the critical value again, okay? So we have our t-distribution, which looks very similar to a normal distribution. So we're just going to use one example of a curve. The degree of freedom is irrelevant when we talk about the critical value because the way that you find the critical value is exactly the same each time. Okay, so if this is our T0 and our alpha is down here, this would be equivalent to a left tail test Okay, so again, instead of z0, we have z sub 0, we have t sub 0, where here's your level of significance, okay? And you're talking about a rejection region. And if you remember from the last lecture, we said the rejection region is anything, any t value that's going to fall within this region over here, okay? Any t value that falls within that region, I'll mark it off a little bit more clearly. Any t value falling within this region over here, this is the rejection region, okay? So if your t value falls so that it's less than your t sub 0, then this would be the case where you would reject the hypothesis, right? The null hypothesis. Then you have your right tail test. Same thing as for a normal distribution. So here now, this is your t sub 0. This is your alpha. Your rejection region is to the right of t sub 0 instead of to the left. So when do we reject the null hypothesis? When t is greater than t sub 0. And this is our right tail test. And then finally, we have our two-tail test. And remember that we're talking about mean, so let's even put in a little bit more here. Well, let's do the two-tail test first. Okay, so our two-tail test, again, we have our t distribution. Remember, your t distribution is symmetrical about the mean. And what that means is that we have, this is t sub 0, but it's negative. And this is t sub 0, but it's positive. And over here, we have 1/2 of alpha and 1/2 of alpha. And our rejection region is anything that's in here. Okay, I'm gonna put arrows here just to make this clearer. This is alpha over 2, 1/2 of alpha. This is also alpha over 2. I think the words got a little bit lost. Okay, and our rejection region here is either our t is going to be less than negative t sub 0, or our t is going to be greater than positive t sub 0. Those are our two rejection regions, and that's our two-tail test. Now, we talked about this before, the way that you can reject or fail to reject a null hypothesis. So that's why you need the null hypothesis. The alternative hypothesis is the opposite, okay, of the null hypothesis. And we use it to identify, well, what kind of tests are we doing? So a left tail test would be H sub A. We're saying that our mean is less than some number. In the right tailed, we're saying our mean is greater than some number. That k is just the some number. And in a two-tailed test, we're saying that our mean is not equal to some number. Okay. So how do we find the critical value? It's going to depend on what test. And when I say that, I mean, how do we find the critical value in the how do we find the critical value in the t-chart? These things in orange, I'll put that in here. What you see here that I put in orange, these are the rejection regions that we talked about in the last lecture. I apologize for not organizing this a little bit better. Hopefully it's clear. If it's not, then obviously just send me an email and I can clarify the picture for you. Okay, so these are each of these are rejection regions that we have. Okay, that's what the t is less than negative t0 or t is greater than t0. Okay, so let's talk about how we find this in the t-chart, and it's nice and simple. And we'll do a little bit of practice. So if it's a left-tailed test, you're going to use the one tail column, and you'll see what we mean by that for alpha. And you're going to put a negative sign. In front of your t-value. So I'm going to write down what to do first, and then we'll go to the chart and take a look. Then for your right tail test, you're also going to use the one tail, right? Because there's only one tail. In right tail test and left tail test, we only have one tail. So once again, you're going to look at the one tail column for that level of significance that you're given. And you're going to put a positive sign, meaning you're essentially keeping exactly what you see in the t-chart because all of them are positive. And then for the two-tail test, there's a two-tail column. With your level of significance specified. And you're going to put both a positive sign, which will give you your positive t sub 0, and a negative sign, which will give you your negative t sub 0. In front of your t-value. So I'm gonna remind you of what the t-chart looks like, and then we're just gonna do some examples of finding that critical value. Okay, here's the t-chart. And you could see here that we have our level of, so the level of confidence is for the confidence interval, okay? What we're looking at is we're looking at the these rows where you see one tail and two tail. So for the left tail test and the right tail test, you're going to be looking at these top numbers, okay, at the 0.10, 0.05, 0.025, 0.01, and 0.005, okay? And for the bottom, for the two-tail test, you're going to be looking at this bottom row. So you're looking at the 0.2, 0.1, 0.05, 0.02, and 0.01. Okay, that's what they're saying that you should do. So a right tail test, if your alpha is 0.1, you're looking at this column right here. For a left tail test, if your alpha is 0.025, you're going to be looking right here at this column. If it's a two-tail test and your alpha is 0.02, you're going to be looking at this column here. So two-tail test, we look at the bottom. One-tail test, we look at the middle. Okay, The top row is what we were looking at when we were doing confidence intervals. And then you go to your degrees of freedom, okay? Now, if your degree of freedom is not in the chart, so for example, the number 57 is not in the chart. So if your sample size is 58 and you have 57 as your degree of freedom, then go to whichever is closest. Go to whichever t value is closest here, whatever degree of freedom is closest, okay? Okay, so let's just do some examples. Of finding critical values, just to make sure that you're comfortable using this chart, okay? And then once you're comfortable using the chart, we can do the hypothesis test for the mean. And actually on the previous page, I'm going to just add to the bottom there that if your degree of freedom is not in the T chart, choose the closest degree of freedom. Okay, this is because sometimes we don't choose these nice, neat samples that are always so perfect and are always in the chart, right? A lot of times when we were going to the z-score chart and we were looking at areas, the area that we wanted wasn't always in the chart, so we went to the one closest. Same thing is true here, okay? So here, we're doing examples of finding critical t-values. So we'll just do 3 of them because we're also going to be doing it for, we're also going to be doing it when we do the t-tests. Okay. So let's find the critical t-value. For a left tail test, notice you need to know which test it is so that you know whether you should be going to alpha or so that you know which row you should be looking at, alpha or for the one tail or alpha for the 2 tail. And you need to know 2 things. You need to know what your level of significance is, and you need to know what your degrees of freedom is. So you're never given the degrees of freedom, right? You're given the sample size. So okay, we'll put our answers in black. So the first thing that you want to do is, we know that the sample size isn't in the t-chart, so we have to figure out our degrees of freedom. So our degrees of freedom is equal to n minus 1, or 21 minus 1, or 20 here. Okay. This is a left tail test, so we're going to go to the T chart. We're going to look at this second row here so that we know which column to go to. So our alpha is 0.05, so we're in this column. Okay, you can see the 0.05 here. We're in this column. Which row we go to? Well, we know that our degree of freedom is 20, so we're going to go all the way down here. And we see the number 1.725. Now, when it's a left tail test, we make it negative. If it's a right tail test, we keep it positive. If it's a 2 tail test, then we would have 2 critical values. 1 is positive and 1 is negative. So here, this is left tailed. So our critical value, our critical T value, is negative 1.725. So it's negative because it's a left tail test. Okay, let's find a critical value for a right tail test. So again, we're dealing with T values because we don't know the population standard deviation, okay? Just like in confidence intervals. For the z-score, for the critical value being a z-score, that would be if the mean is known, if the standard population standard deviation is known, or you'll see in the next lecture, just like before, if we are doing population proportions. Okay, so there's nothing new here. So we're going to find the critical value for a two-tailed test. We'll do right-tailed next. And in this one, our alpha is equal to 0.01 and our n is equal to 15. Okay, so for this one, again, you have to identify your degrees of freedom. So that's 15 minus 1, which is 14. And we're going to be going to the two-tail column. It's a two-tail test. So let's go in and so we're looking at this bottom row here to figure out which column. So our alpha is 0.01. So the column that we're using is the last one. 0.01 over here corresponds to the two tails. Okay. So we go to 0.01 and then we're going down to degree of freedom of 14. Okay. And we get 2.977. So we have two T zeros. Okay. 2.977. That's our positive. And then our negative is negative 2.977. Okay, and remember our critical region would be that our T is greater than 2.977 or our T is less than negative 2.977. Okay, those would be our rejection regions. We call it a rejection region because that's when we reject the null hypothesis. Okay. Okay. So again, we have two critical values because it's a two-tailed test. Okay, and finally, let's do a right-tailed test. So you could see that the test is just telling us positive or negative, essentially. So we want to find the critical T value for a right-tailed test. And this time our alpha is going to be 0.005 and our n is going to be 11. Okay. So once again, and you should try this on your own. You should pause the tape right here. Try it on your own. Make sure that you can use the T-chart. Do a few of them, okay? So let's go to the T-chart again. or even before we do that, we have to find our degrees of freedom, right? So our degrees of freedom is going to be 11 minus 1, or 10. And here this is a one-tailed test. So we're going to go to the one-tailed row, and we're going to look at for 0.005, which is this last column here. Okay, so notice we're looking at the one tail. So it's this last column. And then we're going to go down to the row that we want. And we're looking at the degrees of freedom for that. So we're going to go down to 10. And we get 3.169. Now this is a right tail test, so that 3.169 remains positive. Okay, so what that's telling us is T sub 0 equals 3.169, and it's positive because it's right-tailed. And just to give you, I'm not going to write these down, but just to give you a little bit more practice, if we were doing a right tail test with a level of significance of 0.1 and our degrees of freedom was 6, okay, 0.1 right tail test, degree of freedom of 6, it would be a positive 1.440, okay, positive because it's right-tailed. If we were doing a left-tailed test with a level of significance of 0.025 and degrees of freedom 12, well, it's left-tailed, so we go to the one tail. Degree of freedom is 12 and level of significance is 0.025. So we're going to this column here. We're going down to 12. Now it's left-tailed, so it's going to be negative 2.179. Okay, negative 2.179. If we were doing a two-tailed test with a level of significance of 0.2, okay, that means a 20% chance that the sample statistic, that the test statistic falls within that region, okay? In other words, 20% chance that it's an anomaly, okay? So here we're going to go to the two-tailed test. It's 0.2, and let's say that our degree of freedom was 30. We're going to go all the way down to 30 for the degree of freedom, and we get to 1.310. So our critical values are going to be positive 1.310 and negative 1.310, okay? So two-tailed test, we're looking here at this bottom row. One-tailed test, we're looking at the middle row at whatever our alpha is. And then we go down to the degree of freedom, okay? Okay. So let's look at the actual t-value that we would find if we were doing a hypothesis test for the mean with the standard deviation unknown. Okay, so this is not the critical value, right? This is just the t-value, just like we had our z-score and then we had our critical z-score. Here we have our t-value and then we have our critical t-value. This is the critical t-value. The critical t-value is what tells you your rejection region. The t-value itself is the standardized test statistic. It's exactly the way that we found the t-value when we were doing this for confidence intervals, okay? Our t-value is x bar minus mu, and the difference is that instead of using the population standard deviation, we use the sample standard deviation. And again, the sample must be random. And the population must be normally distributed. Or n has to be greater than or equal to 30. Okay, one of those two. So it has to be a random sample, and either the population must be normally distributed or n has to be greater than or equal to 30. Okay? Okay. So how do we perform the hypothesis test? Now, this hypothesis test, when our mean is unknown, we said that sometimes when the mean is, not the mean, I'm sorry, standard deviation. When the population standard deviation is known, we said sometimes this hypothesis test is referred to as a z-test. For this, when the standard deviation is unknown, we refer to it as a t-test. Remember, this means that our test statistic is the mean. Okay, and this is going to be exactly what we did in the last lecture. The only difference is that one, we're working with rejection regions, so we're doing exactly what we did at the end of the last lecture, the last two problems that we did. And two, we're using a critical t value instead of a critical z score. Okay, everything else is the same. Okay, so let's go through the process here. Same process. We have to verify that the sample is random. And that the population is normally distributed, or n is greater than or equal to 30. That's always our first step, because if these things are not true, we're done. We can't move on to that second step, because then this doesn't, we can't use this t sampling distribution. Okay, we're using this t distribution. We can't use it if these things are not true. Second thing that we're going to do is we're going to state our null hypothesis and our alternative hypothesis. And you're going to identify the claim, right? You want to know which one is your claim. You're going to specify your level of significance, and you're going to determine the degrees of freedom. And like I said, your level of significance is given to you if you're being given a problem to work out. And the degrees of freedom, the sample size, is given to you. So some of these steps are really straightforward. Okay, the next thing that you want to do is, now that you have your degree of freedom and your level of significance, you can determine your critical value, okay, which will give you your rejection region, okay? So you have to use your T-chart. And remember, you have to know which test. And that test depends on your alternative hypothesis. So you're finding the critical region. This is just so that you know when to reject and when to fail to reject. We also call this the rejection region. So I told you I would use it pretty interchangeably. Okay. We're just using T sub 0 instead of Z sub 0, like we did in the last lecture. So left-tailed. We wrote this down already, but I'll have it here so that you have it. Would be if your T value, your standardized test statistic, is less than your critical. A right-tailed test would be if it's more. And a two-tailed test would be if your standardized statistic is either less than negative T sub 0 or it's greater than positive T sub 0. Okay. And then you're going to find your standardized test statistic. You're going to find your T. So your test statistic is the mean, okay? It's your sample mean, but you're standardizing it. That's your T. And finally, your last step is to make a decision and write a conclusion. Okay, our decision is whether or not we reject the null hypothesis. And our conclusion is what we're saying about the claim. So maybe we're supporting it or rejecting it, right? We're supporting it. We can support if it's H sub A. Okay, if our claim is H sub A, we're either supporting or saying that we're failing to support. If our claim is H sub 0, we're saying we're rejecting or failing to reject. Okay, so let's just put that chart in there one more time. Just so that you have it to refer back to. This is, once again, I guess sometimes that's not so easy to remember. But if you remember, it's not that hard to remember either. Because if you remember that you can only support or fail to support, okay, then you know that if you're failing to reject, the null hypothesis, then that means that your alternative hypothesis you're not supporting, okay? Because you're failing to reject the null, so your alternative, you can't accept the alternative if you're failing to reject the null, okay? So let's just, again, let's put that chart in here. So your claim, either your null hypothesis is your claim, or your alternative hypothesis is your claim. Then you have your decision. So either you reject the null hypothesis, or you fail to reject the null hypothesis. And we said if your null hypothesis is the claim and you're rejecting it, okay, then you're rejecting the null hypothesis. You're saying it's incorrect. Okay. If you're failing to reject, all you're saying is that you're failing to reject the claim. So there's not enough evidence to reject it. This doesn't mean that you're supporting it. Okay, I always go back to that, to a jury. If you find a defendant not guilty, which would be the same thing as failing to reject the null hypothesis, that does not mean that you're saying they're innocent. You're just saying there wasn't enough evidence that they were guilty. Okay? And if you reject the null hypothesis and the alternative is your claim, then you're supporting this claim. This is the case where you're saying you're right. You can only say you're right if the claim is the alternative hypothesis. You can only say you're wrong if your claim is the null hypothesis. And here, again, you're not saying that the claim is wrong. You're just saying you don't know. Okay. Okay, let's do a few examples. Okay, so let's say that a used car dealer says that the mean price of used cars sold in the last year is at least $21,000. Okay. You suspect that this claim is incorrect. So you're going to test it. You take a random sample of 14 used cards. in the last year. So notice again how specific our studies are. This should have a sold, right? 15 used cars sold in the last year. And you find that the mean price, so this is a sample mean, is $19,189. Okay, you also find that the standard deviation, which is S, is $2,950. Okay, remember S is the symbol for sample standard deviation. Okay, you want to know, is there enough evidence to reject the dealer's claim if the population is normally distributed and the level of significance is 0.05. Okay, so let's work through this same way that we work through all of the other problems, okay? We have to first make sure that this is a problem that we can solve. So we're going to, I'm going to go back for a second. And the reason I'm going back is I say verify that the sample is random and the population is normally distributed, or n is greater than or equal to 30. I just want to point out that you also want to verify that the sigma is unknown, because if it's known, you're going to use z-scores, right? You're going to use a z, we would refer to it as a z-test. Here you're using a t-test. So I would just keep that in mind as you go through these, okay? So our first step is to do that verification. So the sample is random. The population is normally distributed. And we're not given a population distribution, standard deviation. So our sigma is unknown, which tells us we're using this t-test. Okay, that's the only thing that that will do for us. If sigma is known, then we're doing the z-test that we did in the last lecture. Okay. Okay, second thing that we have to do. We have to state the null hypothesis and the alternative hypothesis. So remember I told you that this could be, the way I usually do this is I look at the claim, and that helps me figure out which to do first. So the claim here is that the mean price is at least $21,000, okay? At least $21,000. So at least includes the 21,000, which means that that is the null hypothesis because we're going to have an equals, okay? So our mean is greater than or equal to 21,000. And this is our claim. The opposite of that is less than 21,000. Okay, at least is greater than or equal to. Okay, next thing that we have to do. We have to identify the level of significance and the degrees of freedom. So the level of significance is given to us. It's 0.05. The degrees of freedom is our n minus 1. So if we go back to the problem, we see that it's a random sample of 14 used cars. So 14 minus 1 is 13. So now we go and we do our critical value. Okay, so in order to find the critical value, we have to know what kind of test. So we go to H sub A, and this is a less than sign. So the less than sign tells us this is a left tail test. I don't know why I did that. Okay, it's left-tailed because mu is less than. Okay, that's how we know it's a left-tailed test. So now we go to our t-chart, and in our t-chart, we're looking at the one tail because it's a one-tail test. We're looking for a level of significance of 0.05, and we're looking for degrees of freedom of 13. So one tail, level of significance of 0.05, that's the second column here. And now we're going to go down to 13. 13 gives us 1.771. Now it's left-tailed, so it's negative. So now we want to identify our rejection region. A rejection region is if t is less than t sub 0 because it's a left-tailed test. So if we find that our t is negative 0.1 is less than negative 1.771, then we're going to reject our null hypothesis. This is our rejection region or critical region. So now we have to actually find our t value, right? So our t value is that x bar minus mu over, and it's t instead of z, so it's s instead of sigma. So we have x bar we found to be 19,189. Mu, it comes from the null hypothesis. Remember, we're assuming that the null hypothesis is true. Standard deviation is 2950. And then we're dividing by the square root of 14. So remember that you're putting an n over here, okay? And if we calculate this, and you should try doing this so that you can practice using your calculators, you get negative 2.297, okay? So when you do this, if you do it in your calculators, remember, you put your numerator in parentheses and your denominator in parentheses, okay? Otherwise, do it one step at a time. First, do the 19,189 minus 21,000, and then do the 2950 over the square root of 14, and then divide those numbers. So either do it in small steps or make sure that you're using parentheses around the numerator and the denominator. Okay, so now we have to make our decision. So negative 2.297 is less than negative 1.771. So t is in the rejection region. What does this mean? We reject the null hypothesis. And if we're rejecting the null hypothesis, what we're saying is that the claim is wrong. Okay? The dealer is wrong. The mean price of the car is not 21. It is not at least 21,000. Okay? Okay, let's do another one. We'll do two more. Notice this doesn't take that long, and it's not that difficult once you have each of the steps down. Most of the steps, you're just identifying things that are given to you. Okay. Okay, an industry analyst says the mean age, we like used cars, of a used car sold in the last year is less than 4.1 years. A random sample of used cars. We'll take a random sample of 25. And again, we have to take a random sample of the same type of car, so they have to be sold in the last year. This shows a sample mean of 3.7 years. I'm sorry, this is totally in your way. And a standard deviation of 1.3 years. Okay, so we want to know, is there enough evidence to support the analyst's claim if our level of significance is 0.10 and the population is normally distributed. Okay, so once again, we're going to go through each of the steps. You should try this on your own at this point. Try doing it on your own. So we've only done one example here, but we've done 2 examples in the last lecture. We were just using z-scores instead of t-values. Okay, so you should try and go through each step on your own and see if you could do it, and then you can come back, start the tape again, and make sure that you're getting the answer correct. Okay. So the first thing that we want to do is we want to identify all of those things, verify, or verification. We want to verify that the sample is random. We want to verify that the population is normally distributed, or n is greater than or equal to 30. So n is only 25, but the population is normally distributed. And our sigma is unknown, which means do a t-test. Then we're going to state our null hypothesis and our alternative hypothesis. So we have an h sub 0, or h naught, and an h sub a. So if we go back to the problem and look for the claim is that the mean age is less than 4.1 years. So less than does not include an equals, which means our claim is the alternative hypothesis. So our mu is less than 4.1. This is our claim. Okay, and then the opposite of less than is greater than or equal to. Now we're going to identify our level of significance and our degrees of freedom. So our level of significance is given to us as 0.10. Our degrees of freedom is our sample size minus 1. So the sample size is given to us. It's 25. So our degrees of freedom is 24. Now we have to find that critical t value. So we have to figure out what test it is, okay? So once again, this is a left-tailed test, okay? It's left-tailed because this is a less than sign. Easy to remember, less than is left-tailed. But also think about the diagram, right? On the diagram, if you're talking about the left tail, you're talking about the values to the left or the values less than, okay? So this is a left-tailed test. Once again, that's because we have mu is less than, okay? And that means that we're going to go to our t-chart. We're looking for the one tail. We're looking for 0.05 because that is our, sorry, 0.10. That's our level of significance. So it's going to be the first column. And we're going to go down to 24 because that's our degree of freedom. So if we go all the way down to 24, we get 1.318, okay? So that's our critical T value, and it's left-tailed, so we're going to put a negative sign in front of it. So it's negative 1.318. That's our T sub 0. Now we're just going to identify our rejection region. So again, rejection region left-tailed means it's less than. Now we have to figure out, are we in our rejection region? So to do that, we have to find the actual T value. It's the distance from the mean. How many standard deviations from the mean are we? So our X bar, our test statistic, remember the test statistic is the sample mean, and then this is our standardized test statistic for every, because it works for every T distribution, okay? So it's going to be 3.7 minus 4.1 over 1.3 divided by the square root of 25. And we get negative 1.54. So now we make our decision. So negative 1.54 is less than negative 1.318. We are in the rejection region. If it were greater, we would be outside the rejection region, okay? And so because we're inside the rejection region, we reject the null hypothesis. And when we reject the null hypothesis and the claim is the alternative hypothesis, we're saying this is wrong, this is right. Okay, so we support the claim. Okay. Now don't forget that this doesn't mean that we're never wrong. We might be wrong. That's the type 1 and the type 2 errors from the first lecture in hypothesis tests, right? That we could have a type 2 error where we're actually say that something is right when it's actually not right. So we're saying that where we say that we reject the null hypothesis, but it's actually correct. Okay, so if we made this conclusion incorrectly, it would be type 1 error. Okay, this would be a type 1 error. Rejecting the null hypothesis incorrectly is a type 1 error. Not rejecting it incorrectly, so failing to reject it when we should have, would be a type 2 error. So here we're rejecting it. If this is an error, it's a type 1 error. The same thing would be true for the last problem, because again, we rejected it. If we shouldn't have rejected it, then it's a type 1 error, okay? Okay, one more, and then that'll be it. So let's say an industrial company claims that the mean pH level, remember, I don't know if you remember from high school chemistry, if you ever took high school chemistry, this is a long time ago for me, but pH level has to do with how acidic something is, okay? The pH level of water nearby is 6.8, okay? So you go to that river and you randomly select 39 water samples. And you measure the pH level. Okay. You find that the mean is 6.7 and the standard deviation is 0.35. You want to know, is there enough evidence to reject the claim? And your level of significance is 0.05. Okay, so let's go through each step. First step is our verification, right? So we know it's a random sample. Now, what you're going to see that's very conspicuously missing is that we don't see that the population is normally distributed. So we have to look at that n, and our n is 39, so our n is greater than or equal to 30. And our standard deviation, our population standard deviation, is unknown. What does that tell us? It doesn't mean that we can't go ahead with the test. It just means it's going to be a t-test instead of a z-test. Okay, now we have to do our null hypothesis and our alternative hypothesis. So let's take a look at what claim is being made. It says the level of water in a nearby river is 6.8. That's an equal to, okay? Is equal to. So that's the null hypothesis because it has an equals. And the null hypothesis in this case is the claim. So the opposite of equals is not equal. That's our alternative hypothesis, okay? Level of significance is given to us. It's 0.05, and our degrees of freedom is our n minus 1. 39 minus 1 is 38. Then we have to figure out what kind of test it is. So our alternative hypothesis is a not equal to. So not equal to means that we have a region and it's outside that region, and that region, okay, is in the middle. Okay, the not equal to tells us it's a two-tailed test. Because of the not equals. Okay, and now we have to go to our t-chart, and we know that we're looking at the two-tailed test row, and we're looking at a level of confidence of 0.05. So two tails, 0.05, brings us to the third column. We're going to go all the way down to 24. Sorry, to 38. So if we go all the way down to 38 at 0.05, so we're in this third column here, we get a critical t-value of 2.024. 2.024. So our t sub 0 is 2.024. And our negative t sub 0 is negative 2.024. So what are our rejection regions? Either t is less than our negative t sub 0, or our t is greater than our positive t sub 0. So either t is less than negative 2.024, or t is greater than 2.024. This is our rejection region. Notice we're breaking this up into very tiny steps. Sixth part. In order to figure out if we're in our rejection region, we have to find the t-value. Notice I write out the formula every time. You don't always have to do that, but it's never a bad idea just to keep it straight in your head even. Okay, so you found the sample mean to be 6.7. The null hypothesis says it's 6.8. You found the standard deviation to be 0.35 in your sample. And you're taking the square root of n. N is 39. So what do we get? We get negative 1.784. So negative 1.784 is not less than, okay, it's not less than negative 2.024. It's certainly not greater than positive 2.024. This is outside the rejection region. Okay, I can write in here that it's not greater than. Seems like it would be obvious because one is negative, one is positive. But it's not either of those things. So this means we don't reject, or we fail to reject, the null hypothesis. And remember, this does not mean that we support the claim. We just say we don't have enough evidence to support we don't have enough evidence to reject the claim, okay? It doesn't mean we support it. Failing to reject is different than saying you're right. It's just saying we don't know. We don't have enough evidence to say it's wrong. Okay, so just in sum, what we do here is we figure out what the rejection region or the critical region is based upon the level of significance and the sample size. Okay, that's going to tell us what the rejection region is. The reason why we need the sample size is because it's degrees of freedom. It tells us which t-distribution we're using, which curve it is, okay? So we find that critical region and we try and determine if our sample, our test statistic falls within that critical region or outside the critical region. If it's outside, we fail to reject the null hypothesis. If it's inside, then we do reject it, okay? And we're using the standardized test statistic that we're using is going to be based on whether the sigma is known or unknown. If it's known, then we're going to be using z-scores. If it's unknown, then we're going to be using these t-values. Okay, so that's what we've done so far. And in the next lecture, we're going to be looking at, in these last two lectures, we looked at how to do tests for the mean. In the next lecture, just like in confidence intervals, we're going to look at how to do tests for population proportions. Okay, so this is it for today. So it may take me a second to stop the video so you can just stop listening now.